Assalamu alaikum warahmatullahi wabarakatuh. My name is Kairun Zulaika from 4 Irshad, and in this video presentation I'll be presenting my PBL research report on rocket launching technology in relation to water rockets. The contents of this presentation consists of an introduction, an elaborate explanation of the principle of conservation of momentum and rocket launching technology, and lastly the design and build of water rockets step by step. In this report, I have gathered evidence on my research regarding rocket launching technology based on the principle of conservation of momentum. This research branches into my attempt in designing and building an actual water rocket. I will also be elaborating and supporting the evidence I found while applying the principle in water rocket launching technology. The first topic is the principle of conservation of momentum. I have included a link of a very useful video in understanding the conservation of momentum, and I highly encourage the students to take some time watching it. But first, I'll explain briefly on momentum. Technically, momentum is the quantity of motion of a moving body measured as a product of its mass and velocity, but it is also often described as an object's tendency to remain in motion. Also, every moving object has momentum. After understanding what momentum is, I will explain on the concept of conservation of momentum. The law of conservation of momentum states that when a system of interacting objects is not influenced by outside forces, like friction and etc., the total momentum of the system cannot change. In other words, the conservation of momentum is an idea which, in a closed system, the total momentum before an event, like a collision, is exactly the same as the total momentum after the event. An example of said event would be in the case of a collision between two vehicles. I'll be explaining collision based on this diagram. A car of mass m1 moving with velocity v1 bumps into another car of mass m2 and velocity v2 that it is following. As a result, the first car slows down to a velocity of v final 1 and the second speeds up to velocity v final 2. The momentum of each car is changed, but the total momentum of the two cars is the same before and after the collision, ignoring friction, of course. m1 v initial 1 plus m2 v initial 2 denotes the total momentum of both masses before the event, while m1 v final 1 plus m2 v final 2 denotes the total momentum of both masses after the event. So how does all these actually apply to rocket launching technology? Let us get into it. What is a rocket? Simply put, rocket is a spacecraft, missile, aircraft, or other vehicle that obtains thrust from a rocket engine. As you can see in this diagram, this is the Soyuz TMA-9 spacecraft that is currently in the picture launching, and you can see the large clouds of smoke produced in accordance with the propulsion system, which we'll get into later. Its structure and composition. First off, the payload system. It acts as a carrying capacity when uninitiated. The types of payload depends on the mission of the rocket. It can be cargo, satellite, space probes, or a spacecraft. Then, the guidance system. It ensures the intended trajectory of the rocket with the help of onboard sophisticated computers and sensors, as well as radar and communication systems to maneuver the rocket while in flight. Lastly, the propulsion system. If you notice, the majority of the entire length of a rocket is actually made up of the propulsion system. It consists of components that facilitate the launching of the rocket off the ground via the nozzle, thus allowing it to be able to propel the rocket in a given direction. The workings of a rocket. Propulsion system. Stored fuel and oxidizer are burned in a combustion chamber. The chamber produces large volumes of exhaust gases at high temperatures and pressures. The gases are exhausted through the nozzle, which accelerates the flow. Thrust is then produced according to Newton's third law of motion. As the gases are pushed out of the motor through the nozzle, an equal but opposite force is exerted on the rocket. Next, most importantly, conservation of momentum in rockets. Before the rocket's launch, the momentum of the system is zero, as the velocity itself is zero. After the launch, the momentum of the system is also zero. As the momentum is zero after launch, the momentum of the exhaust plus momentum of the rocket has to equal zero. The momentum of the exhaust is equal in magnitude to the momentum of the rocket, but opposite in sign because it's the opposite direction. After all that, I'll apply the principle in designing and building a water rocket. Materials and apparatus. For this project, I made a water rocket but didn't get to launch it, so I'll be explaining the concept and how it relates to conservation of momentum briefly. At the side, you can see a schematic diagram on how I'll structure the rocket, but in this diagram, I didn't include the ballast. Firstly, nose cone. It's made of paper and gives more stability while in flight. Second, pop bottle. Use a bottle of any type, preferably a soda bottle. Acts as a body that contains pressurized air and water that can later be released, producing thrust. Next, the fins. It's made of cardboard and shaped to trapezium-like shapes. I didn't remember to correct that, I'm so sorry, which then attached to the sides of the bottle. It aids in aerodynamic stability while in flight. Next, the ballast. The ballast is the one that I didn't add, but if it's there in the schematic diagram, it will be inside the nose cone right here. The ballast adds mass to the rocket to increase stability. Then apparatus includes duct tape, scissors, or a knife. Besides building a water rocket, designing it is also quite vital to how it will function later on. So I'll present some design aspects which I took into consideration while building this water rocket. Firstly, the size or volume. The volume of the rocket determines the maximum amount of energy that can be stored in the compressed gas. The energy is proportional to both the pressure and the volume. So in order to increase the total amount of energy available, it is necessary to use a larger rocket. Second, the weight. The lower the weight of your water rocket, the better it will fly. The distribution of weight on the body of the rocket influences the aerodynamic stability of the rocket while flying. An aerodynamically stable rocket flies with its nose first and should have a flight trajectory like a beautiful smooth arc, as you can see in the diagram A. An aerodynamically unstable rocket may start out with its nose first, but its flight will quickly become unstable and it will flap and tumble in the air and then simply fall to earth, as you can see in diagram B. Aspects of a water rocket. These are the features that exist in water rockets and how it contributes to its workings. First off, compressed air and water. The bottle is half filled with water and then pressurized with a gas, usually air compressed from a bicycle pump. When the bottom nozzle is opened, the internal air pressure forces the water out of this nozzle at high speed, causing the rocket to shoot straight up at high velocity. Secondly, nose cone and fins. The nose cone reduces air resistance as the rocket flies through the air. Fins stabilize the body of the water rocket, reducing air resistance, thus allowing the water rocket to be able to fly higher. Lastly, the ballast generally helps in providing better stability to the body of the rocket, as proper weight distribution is vital to the aerodynamic stability while in flight, as we have covered in design considerations. Lastly, I'll explain step by step on how to make a water rocket. Since I didn't actually launch it, I won't be showing any launching photos. First step, we cut 3 fins out of the cardboard. Cut a trapezium-like shape referred to the picture, then adjust the shape according to the bottle. Then cut 2 more identical ones. Next, cut fringes on another bottle's top. Choose an appropriate sized water bottle or soda bottle, then cut it into a third of its size. After that, cut the bottom circumference into fringes, as you can see in the picture here. Next, we make a ballast. Use any heavy materials to act as a ballast. In this case, I use crumble heavy paper. Other alternatives can be a plasticine ball or a tennis ball. And then we place the ballast inside the nose. Place the ballast inside the cone, then seal the cone securely so as to ensure a more secure construct to the rocket. The secure construct will allow the rocket to be flying without any difficulties, such as maybe the nose cone might get off while it's flying or something like that. So it's really vital to make sure it's secure. Next, attach fins and then proceed to launching. After securing the ballast, attach the fins securely with tape. This also goes the same like the ballast. You have to really secure the fins because it's a very vital aspect of the rocket. So you really need it to be secure so that it doesn't come off when it's flying. Okay, and then proceed to making the launcher. Add pressurized air and water, and then launch away. Thank you, and that's all for the slideshow. Assalamu alaikum warahmatullahi wabarakatuh.